Okay, fine. So this is our last lecture, and today we will see the matching. So first I share my screen. Okay. So the screen is visible, right?
Yes, sir.
Okay, fine. So we start matching. So what is the definition? So let G, the pair V and E, be a graph. Okay. Then a matching in G is a set of edges, say M, which is subset of E, such that for every edge, say EF from M, okay, so E and F are not adjacent. So that's all. So for an example, so if we take, say, this picture, so this one is my graph G. Okay, so these are the vertices and the remaining are the edges. Okay, now if I take, say, this one and this one, if I take this collection, okay, this edge, say this is my E and say this is my F. Now the collection M, E comma F, that is a matching, right? Because it satisfies the property. That's mean if you take any two edges, so we have only two edges, say E and F, and they are not adjacent. So this is a matching. So another example is, so if we take this graph, similarly, okay, this one. Now if I take these three edges, say this, and this. Now again you can check that, right? The red edges are not adjacent, so this is a matching. Okay, so this is a matching. Now what if I take this one and say this one only, these two. Now this is also a matching, right? Now the question is, now if we take this matching, can you add some extra edges in that matching?
No, sir.
No, right? Now we define two terms, one is maximal and one is maximum matching. So maximal and maximum matching. Okay, so a matching M in G is said to be a maximum matching if M has largest cardinality So among all possible matching of G. Matching of G. So this is called maximum. And what is maximal? So a matching M in G is said to be a maximal matching if no proper superset of M is a matching of G. Okay. So for an example, the green one. So if you take only this edge and this edge, okay. Now clearly we cannot add more edges, right? In that matching. So this is a maximal matching. Like I should reverse the color anyway. So green one. So maximal matching. Okay. And if we take say this one, okay, can you tell me what is the maximum matching here? Or what is the cardinality of the maximum matching?
3.
3. So we can choose these 3, right? And this is called a maximum matching.
So can we say also that it is also a maximal matching?
Right, right. It is also a maximal also. Maximal as well. In fact, any you can say that any maximum matching is also a maximal matching, right? But not conversely. But a maximal matching may not be a maximum matching. And note that maximal and maximum they may not be unique, right? And this is another observation is that maximal and maximum matchings may not be unique. Okay. By the definition, you can easily say that any maximum matching is a maximal matching as well. Why? Because you cannot add more edges. And here this is a maximal matching, but it is not a maximum because it has cardinality 2. But we already have another matching which is cardinality 3. So this one, the left one cannot be maximum. So that is trivial actually. These definitions are very easy and it follows from the definition. Okay. Now there is another term which is called a perfect matching. Now what is a perfect matching? So a matching M is called a perfect matching. It's called a perfect matching if it covers all the vertices. Okay, if it covers all the vertices. Okay, so for an example, so in this figure, can you tell me what is the maximal, what is the perfect matching? Is there any perfect matching here?
So the maximum
The
matching is
second
a
one,
perfect
maximum
matching.
matching.
Yeah, the right one, right? But so can you say that any maximum matching is always a perfect matching?
No, sir.
No. So can you give one example, quick example?
So in the other one, if we add one more age in the
Yeah,
left
we can
of the
just take the
corner.
odd cycle. We can just take the odd cycle, right? So we can take just, oops, it's 6, sorry. We can take just odd cycle. Now you can see that. So this, right? So this is a matching and this is a maximum matching. Right? And of size 2. So this is a maximum matching of size 2. So if you take any odd cycle, then it has a maximum matching, right? Which is not a perfect matching. Okay. Now can you give any necessary condition for the perfect matching? So if you have a perfect matching, then what can you say about the number of vertices?
It's 2 into the cardinality of that cardinality of the matching, the cardinality of M.
Cardinality of M? No,
2 into the
M is just a collection of edges.
so the number of vertices will be the 2 into the cardinality of the perfect matching.
Yeah, the twice of, right? The twice of the number of M, right? So therefore it is always even, right? So therefore in a perfect matching, okay, or we can say that not in a perfect matching, if G has a perfect matching M, then that V of G, that's cardinality, is equal to 2 times cardinality of M. So therefore number of vertices is always even, right? Now suppose you have a bipartite graph, say 3, 4. Okay. Now so this is a bipartite graph. So this is one vertex set, this is another vertex set, and you have some matching. You have some edges between this. Now, can you have a perfect matching here? Or equation one extra. So number of vertices is even. Yes. This is now 8.
Sir, if it's bipartite, then both of the, I mean, to have a perfect matching, we need the number of vertices to be equal in both the sets, and
Right.
yeah, that should be the
So
condition.
right. So if G, say L, R, E, we write in this way. This is one part, this is another part, and this is the number of edges. Edges. This is one part, this is another part. Okay. If this is a bipartite graph and has a perfect matching okay, so then the cardinality of L should be same as cardinality of R. Okay, so this is the necessary condition, right? So this is very easy. Why? Because since you have a perfect matching and you have some number of vertices here, say, and this is also say 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, yeah. Then you should have some matching. So this kind of matching, see this with this, right? So therefore, both number of vertices of the both sides should be same. Otherwise, you will have some extra edges. Okay, extra vertices. Sorry. Okay. Now, if you take this graph, okay, now this is a bipartite graph. Now, can you quickly tell me what is the size of maximum matching?
So 4.
It is 4, right?
Yes, sir.
So why it is 4? Because the number of vertices here is 4, right? So therefore, in a bipartite graph, in a bipartite graph, G L R E, okay. So the size of maximum matching is at most this number. So minimum of cardinality of L, cardinality of R, right? It cannot be more than this. Also, this is very trivial. Okay. So now we will actually prove one important theorem. This is called that Hall's marriage theorem. So before that, I define neighbors of a graph. Okay. So let G be a graph. Okay. Now we define, okay, for a set S subset of V, we define its set of neighbors it is denoted by here gamma S. Okay, gamma S means the neighbors of S, and it is a collection of the vertices V such that there exists U belongs to S and UV is an S. Okay, so it is collection of the vertices which are adjacent to a vertex of S. So that's all. So for an example, if we take this graph, say U1, U2, U3, U4. So V1, V2, V3, V4. So this one. Now tell me what is the neighbor of U1? What is the
V1,
V1? Fine. What is the neighbor of U1, U2?
V1, V2,
Right. And what is the neighbor of U1, U2?
V1, V2.
Right. So here neighbor of U1, you can just check. So this is just a singleton set V1. Neighbor of here U2. This is the set V1, V2. And if you take neighbor of U1, U2, that is also the same set V1, V2. Okay. What we can do? Right. Fine. Now there is a lemma. It says that so let G.
Sir,
Yes.
how will I write a gamma for S? Means what will be this set for this graph?
Sorry. Oh,
What
sorry,
will
sorry, sorry, sorry. Right, right. It is gamma. I write it is gamma, right? It is not n.
okay.
Sorry. Sometimes I denote the neighbor by n, and therefore I just miss. So in this here, because in the proof I have seen they use that notation gamma. So therefore I also write the gamma, the notation. You can write any notation. That is not a fixed one. So since every book refer gamma s, so I also write gamma s. But anyway, so you are free to choose any number, not gamma. You can write n as well. Okay.
Sir, these elements can be elements of S, right?
Which
Suppose
one?
neighbor of U1 V1 is U1 V1 itself. It may be possible, right? Or
Yeah,
we did
that
not.
is yeah, that is possible. That is possible in any graph, but it is not possible for the bipartite graph. Means you are saying that gamma s intersection s, that is non-empty, right?
Yes, sir.
Yeah,
Yes,
that
sir.
is possible. That is possible for general graph, but not possible for bipartite graph.
So can be possible for bipartite also. So now if we take one vertex from first one as second vertex from other class, take U1 and V1.
Which one? Okay, no. Actually, okay, fine. So we will write in the other way. So what I got disconnected. Right. Now I got connected again. Now right. That is possible for general graph, but for the bipartite graph, actually we push some additional condition. We take S always subset of L. Okay, then it will not be possible. I'm writing this one. So this is your lemma. So S is this bipartite graph. So let this be a bipartite graph. Right. So with a perfect matching M. Okay. Now then for every set S subset of L, that gamma S bigger equal to this one. Okay. Now, if you choose your S subset of L, then obviously gamma S and S, they are disjoint, right? Now here you can check that S intersection gamma S, it should be empty, right? As gamma S is a subset of R. This is one, and another one is, since it is a bipartite group with a perfect matching, so therefore this cardinality is same as this. Right? Now can you give me a quick proof of this one? So this is very simple proof. This is a very simple one. Yes, can you just give me a quick proof of this? Yeah, just say it is very simple. So you have a bipartite graph.
Sir, we can say that as it is a perfect match, perfect matching. So it is at least connected to the same number of vertices. So that it must be a perfect matching. मतलब, each vertex must be connected to one vertex corresponding to the second
Right,
class.
right. So that is the simple proof, right? So what we can write it is for each or for every set S subset of L, okay, each vertex of S is matched with a unique vertex of gamma S, right, by an edge in M. Edge in M. In other words, you can say that gamma S, if you take this, intersect with that vertex set of M, so that is same as S. Right? So that is the definition of perfect matching, and what you have just said, that every vertex is connected with a unique vertex. And therefore, gamma S is greater or equal to this number, and that is S. So we are done. Now, what do you believe? So do you believe that this gamma S always equal to S, or it can be strictly bigger than S? Yes. So what do you believe that? So gamma S can be equal to, that is, it is always strict, it is always equal to S, or can it be strictly bigger than S as well? Gamma S?
Sir, it can be bigger also, as
Right,
we've shown
right,
in the case of U2 in the above example.
exactly. Here it is 1, and here if you choose S, it is 2, right? So it can be bigger than 1 as well. I mean, bigger than S as well. Okay. Fine. Now we have the main theorem, that is called Hall's-Marius theorem. Now it says that, so let G, L, R, E be a bipartite graph. So with it is given that that cardinality of L and cardinality of R both are same. Okay. And suppose for every S subset of L, okay, we have gamma S bigger equal to that coordinate of gamma is bigger or equal to coordinate of S. Now, if this property satisfies, then G has a perfect matching. Okay, so this is very important theorem. So sometimes you might be asked to solve some problem where you need a perfect matching. Okay, so in that case, you can find it is a bipartite graph with both part have the same number of vertices, and then you have to prove that this one, that is for every subset of L, gamma is bigger or equal to cardinality of S. If you can prove that, then it will follow that G has a perfect matching. And the proof is actually very simple. Proof is actually very simple. We will use induction here. The roughly what you can see here. So say this is your L, this is your R. Okay. Now what is the aim, or what is the actually main part, or you can say that heart of this theorem is, now choose this vertex, say U1. Now what is gamma of U1? That is bigger or equal to 1, right? So therefore you must have one vertex V1 such that there is a vertex. So call this is V1. So you have an edge. Okay. Now you choose U1. Now choose U S equal to your U1 U2. This one. Now again, what is your gamma S? Now gamma S is bigger or equal to 2. Right. So therefore U2 must be joined with another vertex. Not right. Other than V1. Now call it V2. Okay. Now take S equal to, say this is your U3. Now take S equal to U1, U2, U3. Right. Now again, what is your gamma S? Cardinality of gamma, this is bigger or equal to 3. And here you have two edges, two vertices. So therefore U3 must be joined with another vertex other than V1 and V2. Now call that a vertex as V3. Now V3. Now proceeding this manner, you can find a perfect matching. So this is the main part, main portion of this theorem. But we will use some different argument to prove it, and we will use the induction. Is that clear? By this given condition, we can do that.
Yes, sir.
Right? But we will use, so this is not a proof because here we are assuming something, and that argument, yeah, that is valid argument, but it is better to use a proper induction argument. Now what we will prove? Now we will prove by induction. Now we will see a proper proof by induction. Okay, so we shall prove by induction on number of vertices of L. Okay, now say this is N in G. Okay, now obviously the result is true for N equal to 1, right? So if you have N equal to 1, so that's mean your cardinality of L equal to 1, cardinality of R equal to also 1, because they are same. Okay, and since it is given that mod of ns bigger equal to mod of this, so therefore it is exactly 1, and therefore you have a single matching. So the result is true for n equal to 1. Now we assume that, so suppose the hypothesis is true for vertices, or for number of vertices less than this. Okay, so whenever you have number of vertices, or you can say less than n or less than mod n, then the argument is valid. Okay. Now you have two cases. Case 1. So if possible, for every S subset of L with 0 less than cardinality of P, strictly less than cardinality of L, we have gamma S is bigger equal to mod of S plus 1. Suppose this is true. Okay. So if possible, for every proper subset of L, you have this, that is strictly bigger than S. Or you can say that cardinality of gamma S is strictly bigger than S. Okay, then what we will do? Now then we choose a vertex V in L. Okay, now then gamma of this V is bigger equal to what? 1 or 2? That is bigger equal to 1 plus 1, right? 2. So, but we don't need that. We need just one vertex. Now choose one vertex U in R such that UV is an edge. Okay. Now what we take? Now take G dash is the graph G minus this vertices UV. Okay. Now, can you say that G dash is a bipartite graph? Yes. This is a bipartite graph, right? G dash.
Yes, sir.
Okay. Now, for each subset S dash, L dash, what can you say about this cardinality? What can you say about this? Can you say this? Can we say this one? Yes or no? Yeah, say something. Can you say this one?
So I thought it will be only greater than equal to cardinality of S.
Right,
Dash.
right. Why we cannot say this one? What we have done, we have just deleted U and V, right? So it might happen that some vertices of S dash were joined with V. That right? Some vertices of S dash adjacent to V, and we are deleting V. So therefore, this might not happen, but we can say this one, and which was the criteria of the theorem, right? So therefore, by induction, G dash has a perfect matching, say M dash, and thus G has a perfect matching M, which is just M dash union the edge UV. Is that clear to everyone?
Yes, sir.
Okay. So what we have done here, we first assume that for every subset, proper subset S, with this condition we have this one, right? So cardinality of gamma is always bigger equal to cardinality of S plus 1. Okay, that is strictly bigger than S.
So how do we get this? Means are we assuming this condition?
Which one?
This cardinality of gamma of S is greater than S.
No, we are getting this one.
No, no, sir, no, no. In the beginning of the statement, in the case one.
Yeah, it
This
is. We assume that. So first, this is a case one. So what is the given in the theorem? It is given that for every S, gamma S is bigger equal to mod of S, right? Cardinality of S. So we have two cases. One case is gamma S is strictly bigger than gamma S for all S. Okay, and case 2 is there is a S, there is one S where cardinality of gamma S and cardinality of S both are same. Okay, so we are taking one case 1. So case 1 is if possible. That's the reason I have written here if possible. For every S with this we have this property, and then we prove the theorem. Okay, so if this is the possibility, then we choose a vertex U and take a vertex V joining with U, and then we delete the both vertices U and V. Then we have a graph, new bipartite graph G dash with one vertex less, actually two vertex less, but in one part we have one vertex less. And since gamma is bigger equal to gamma S plus 1 in G, so therefore in G dash, gamma S dash is bigger equal to only cardinality of S dash. And therefore by the induction hypothesis, we can say that G dash has a perfect matching M dash. And if we,
Sir,
yeah, yes.
after removing an edge, how we are claiming that the graph is still a bipartite?
Because you have removed just one edge, right? No, not only one edge. You have a bipartite graph, and what you are doing, you are not removing only one edge. Okay, you are taking the
Yes, sir. Yes, sir.
induced graph.
We are removing multiple edges. We are removing two vertices only, one from S and one from the R. So one from
Right,
L and one from R.
right.
So
So
there is possibility that one of the vertex has an edge with some other vertex, and and that vertex has only that edge, means only the edge with one of these vertices.
no, that is not possible, right? Because it is already given it for every vertex, it is bigger equal to 2.
Oh, okay, okay,
Yeah, that is a good observation. That
okay.
is a very good observation. He is saying that it might possible that one vertex is joined with V only. Now, if we remove those edges, right, those vertex V, then the graph can be may have a isolated vertex. He is claiming that, but that is not possible because for a vertex V, gamma S is always bigger equal to 2 in this case.
Okay, sir. Got it.
Okay. Fine. Right. Hmm. Now we'll go to the second portion, case 2. Okay. Now, if possible, for some S with So we are taking proper. We have gamma s equal to this. Okay. So in the case one, we have assumed that for every subset S, proper subset S, we have gamma S is bigger equal to cardinality of gamma is bigger equal to cardinality of S plus 1. And in the case 2, we have assumed that there are some set S where cardinality of gamma S is equal to cardinality of S. So both cases are exhausted, all the cases, right? So this is the another possibility. Now what we'll do here in this case, you have a graph. Say for an example, you have this graph. Say, this one. So you have this and say this one. Okay. Now say this is your S. Now you can check that here S is 2 vertex and gamma of S is just this 2 vertex. So this is your gamma S. Okay. Now what will prove that? Now take two subgraphs of G. Okay. So one is L dash R dash E dash, another is G double dash, which is L double dash R double dash E double dash. Okay, where L dash is your S and R dash is your gamma S. Okay, and here L double dash is your L minus S and R double dash is your R minus gamma S. Okay, so you have these two sets of vertices. Okay, and E dash and E dash are the induced. So E dash and E double dash are induced edges on those vertices. Okay, so now okay, now again the condition is that you are saying that so it is bipartite or not. We will check that. Okay, so first of all you can check first one that G dash L dash R dash E dash. Okay, it satisfies the condition or not. So first of all okay. Now look at this one. Now here R dash equal to L dash. This is clear, right? Because R dash your S and R dash your gamma S and both are same. Okay. And for every gamma S dash intersection R dash. Now what is this? Can you tell me what is this? So what is your R dash? R dash is your gamma S, right? So for every, you can say that is the subset of L dash. We are getting this. It is same as this intersection gamma s and equal to gamma is dash only as gamma is the subset of gamma s, and that is less than equal to this. It is by given condition. By given condition. Oh, sorry, it is bigger equal to that. Now, is this clear with everyone? So why for each S dash subset of L dash, you have this one?
Yes, sir.
Right? Fine. And therefore, so G dash satisfies the given condition. So by induction. Oh, okay. Now from this, you can say that now G dash is a bipartite graph as well. And G dash has a perfect matching. Perfect matching by induction. Okay. So though we do not need that any vertex is isolated vertex or not, because if you take a isolated vertex, that is also a bipartite graph. But here that case will not arise. Okay, that student asked last time, right? So if you have a isolated vertex, then what happens? That will not arise in this case. Okay, so G dash has a perfect matching. Now what we have done, so we have separated G into two distinct parts, G dash and G double dash, right? Now G dash has a perfect matching, and now we will prove that G double dash has also a perfect matching. Now look at G double dash. So look at G double dash. Okay. Now what is G double dash? G double dash is again L double dash, R double dash, E double dash, and here this is same as this, right? Because we have removed same number of vertices. So we have removed S number of vertices, right? That is the cardinality of S. Sorry, we have deleted only the vertex of S and from L, and we have deleted vertices of gamma S from R, and we get L double dash and R double dash, right? So they are same. Now, if possible, now for this we can say that it is a bipartite graph. Obviously, bipartite graph, because any subgraph of a bipartite graph is also a bipartite graph, right? But it does not have, will not have any isolated vertex. By isolated vertex, we will prove now. Now what we can now see that now if possible, for some S double dash subset of L double dash, you have gamma S double dash intersection R double dash that is strictly less than this. If possible, you have this one. Then we will get a contradiction. What kind of contradiction we will get? Now take S, the previous S, okay, union gamma S double, sorry, S double dash. Now take this set. Okay. Now if this is true, then take S union this and take gamma of this one. Okay. Now what will be the neighbor of S and S double dash? See, the neighbor of S are already gamma S, but neighbor of S double dash can be in NS. So we have this property. Okay, so this is your S, now this is your gamma S. Okay, see, if you choose that S, now suppose this is your S dash. Okay, and suppose you do not have this vertex. Then what happened here? What is actually, can you tell me what is gamma of S double dash? What is the coordinate of this? That is,
One.
yes, 1. Now what is gamma S double dash intersection R double dash?
It is 1.
That is 0. S double dash does not have any S from R double dash, right?
Oh, sorry. This one is R double dash, right one. Or the whole is R
That
double
is
dash.
0. Yeah, and it is cardinality of S double dash. Now in that case, what we will do, we will just take S union with S double dash. Okay. Now what might happen that, so for S we are adding gamma S, all of those vertices, this we are adding these vertices. Now it might happen that S dash, S double dash, the neighbor of S double dash may be in gamma S or may not be. Okay. So if it is in gamma S, we have already taken those, and it is not in gamma S, then you have taken that gamma S double dash plus, sorry, intersection R double dash. So this is the condition. So this will be equal to this. Okay. And if this is less than gamma double S double dash as we get here, then that will be equal less than gamma S plus S double dash. And what is gamma S? That is equal to S. So equal to S plus S double dash, and that is S union S double dash. So therefore, if you take here, in this case, you can check that. In this case, if you take S union S double dash, and if you take neighbor, that is neighbor is 2, and that is less than cardinality of S union S double dash, that is 3. So you get a contradiction. Okay, so that's mean if possible for some S double dash subset of L double dash, you have this condition, then you get a contradiction. Okay, so therefore this is not true. So thus for each S double dash subset of L double dash, we must have gamma of S double dash intersection R double dash that is bigger equal to this. Okay, so therefore by induction hypothesis, G double dash has a perfect matching, say M double dash. Okay, so here G dash has a perfect matching M dash, and G double dash has a perfect matching M double dash. So therefore G has a perfect matching M dash union M double dash. So we are done. Did you get the theorem? So what we have done, so if for each set S, you always have that cardinality of gamma is bigger or equal to cardinality of S plus 1, then we just take one vertex, okay, and take each one vertex in addition to that vertex and delete both of them. Then we use the induction. And in the second case, if you have one set S such that gamma S and S has same number of vertices, then we delete both, okay, and remaining graph has the same property. So by induction it has a matching, and the graph induced on S and gamma S has also a perfect matching. So therefore G has a perfect matching. So is there any question here?
The second part I didn't get.
Where
Can
you
you,
did not get?
can you explain please from starting? Just an overview.
Okay. So first what we have done, we just delete what is L double dash, we just delete S from L. And what is R double dash? L double dash is L minus S, R double dash is R minus NS. Oh, sorry, gamma S. Okay. Since S and gamma S has the same number of elements, so therefore L double dash and equal to R double dash. It is fine. So this is a bipartite graph because it is a induced on the bipartite graph. Now we assume that if possible for some S double dash, okay, if this is true, okay, then what we take? We take the set S union S double dash and we prove that the hypothesis is not true. Because if we take gamma, the cardinality of gamma is there S union S double dash. It is not S dash. S union S double dash. Then this is equal to gamma S plus gamma S double dash intersection R double dash. Why this is equal to this? Sorry. Why this is equal to this? Because what are the neighbor of S double dash? They may be in gamma S or may not be in gamma dash. Right? What is the neighbor of S double dash? So this is your S double dash. See that? The neighbor of S double dash either in gamma S or not in gamma S. Now if it is in gamma S, we have already taken here. And if it is not in gamma S, we can write it is gamma S double dash intersection R double dash. So for these vertices. So this is equal to this. And now it is just a set theoretic property. Now this is less than this by the given property here by our assumption. But gamma is equal to S. So therefore this is strictly less than this. And since S and S double dash are disjoint, so this is equal to this. So therefore this is strictly less than this set, which is a contradiction. Okay. And here I have shown it in terms of picture. So suppose you have this type of property, then you have a contradiction. So suppose this is your S and this is your gamma S. This is your S and this is your gamma S. And if you have this kind of graph, so that S double dash intersection S dash is 0, then if you choose S union S double dash, then you get a contradiction. So therefore this type of graph will not exist. Because you must have an edge from this vertex to this. So you must have an edge from this to this. Okay. So
Yes, sir.
since you have a contradiction here, so therefore this is not true. So therefore for each is double dash, you must have this, and this is the given condition. And your L double dash has less number of vertices. So therefore by induction G double has a perfect matching. And if and G dash has a perfect matching, G double dash has a perfect matching, and G has right now G has, if you take those union, then you have a perfect matching for G. So we are done.
By induction means they are using that theorem. Means by induction, what do you mean by induction here? Which induction?
In the beginning I told here what is my induction, you can see what, right. So we shall prove by induction on the number of vertices L. Okay. So we assume that the result is true for n equal so the result is true for n equal to 1.
Yes, sir.
So this is your hypothesis that if G is this one and if this, and if for every vertex this condition satisfies, then G has a perfect matching. Okay, and here we are using the induction on the number of vertices of L. Now if the number of vertices is 1, then this is trivially true. Now we assume that this theorem is true when the number of vertices is strictly less than this cardinality. Okay, so we are using the cardinality, induction on the number of vertices. The last lecture also we have did that. We have done this one. That is, we have
Okay.
used the induction on the number of vertices. And here we are using the number of vertices. We are using the induction on the number of vertices of one part. Okay. Anyway, it is yeah. Just read the proof. If you don't get it, but you should remember what I gave you at the beginning of this one. This is the main idea. Okay. So just keep this one. So how inductively we can construct a perfect matching. And if you understand this, then it is fine. Okay. So this is the main core. This is the main core of this theorem. But we have to give a precise argument, inductive argument. So we have given this. But you should understand the main core. And then if you read, then you automatically will understand the induction part. Okay. Now this theorem has another version. Another version. Now here taken we have taken bipartite graph with this. Right? Now what if you have this one and the same property satisfies? Then what can you say about this? Can you tell me by using the same proof what you have this one, then what you can say about the theorem? Yes.
So a maximum matching of size twice of L exists.
No, not twice of L, of size L.
Of
Because
okay, okay,
right,
yeah,
because
yeah,
matching
edges.
means the number
First,
of edges, right?
yeah, yeah, yeah.
Good. So it is a bipartite graph with, sorry, it is less than equal to R. Okay. Okay. Now then there is a matching that covers L, or you can say that there is a maximum matching of size this if and only if for each S subset of L we have cardinality of gamma S is bigger or equal to cardinality of S. Okay, so the theorem can be applied for both cases. So for this one as well as for this one. For this one we get a perfect matching of size this, and here in this case we get a maximum matching of size L. Okay, so both are important. So as I am saying that this theorem, the both theorem, this part and this part, both are very important for your major as well. Okay, I will try to give a question related to this one. So just practice the problems on that Hall's marriage theorem. So what you need to find, so everything actually will be clear. Just you need to prove that this part, that is for every S, for every each S subset of L, you need to find this one. So this is the main part of this theorem. Okay, so you have to prove that. Okay, since I have 17 minute time, I just quickly go through a application, one problem. Okay, one problem. Now we can write the problem. Okay, since I don't have much time, I can use the slides for this problem. Then I don't have to write. Okay, where it is? This one. Okay, so this one. Now just take a deck of cards, right? You know you have a 52 cards, right? In a playing card, you have 52 cards. Now take that standard deck of cards, and what you do, just deal them into 13 piles of 4 cards. Okay, so that's mean you have 52 cards, and what you do, suppose you have 13 people there, and you just give 4 cards to each 13 people. Okay, now the question is, then it is always possible to select exactly one card, or better to write that, prove that it is always possible to select exactly one card from each piles such that 13 selected cards contains exactly one card of each rank. And what are the rank? They are that as 2, 3, 4, 5, 6, 7, 8, 9, 10, and then Golam, Queen, and King, right? So you have these 13 uh, um, rank, and you have 13 piles, and each pile has 4 cards. Okay. Now what we'll do here? So you have this rank. So list this rank. So 2, 3, 4, 5 up to 10, right? These are the rank. and then you have J, then you have Queen, then you have King, and at last you have S. So these are the 13 rank. Okay. And you have 13 piles. And each piles have 4 portions. Okay. So these are 13. Okay. Now what we'll do, we write these are as your R and we write this is your L. Okay. So these are the points, you can say that. Now you make a graph G L R E where cardinality of L and cardinality of R is 13. Okay. So what is L? L corresponds to the rank. Okay. And R corresponds to the piles, and each pile has 4 elements. And there is an edge. So there okay. And if you take U from L and V from R, then they are adjacent. If the pile corresponds to V, okay, contains the rank corresponds to U. Okay. So that's mean 4 and this point will have an edge if and only this 4, the at least one card of 4 lies in this one, in this portion. Is that clear? And 5, from 5 you have an edge here if and only if the card 5 is in there. Okay. Now from this, can you tell me what are the degree of this point? What is the degree of this point?
At most 4.
Yeah, at most 4. It can be 1 as well.
Yes, sir.
Why it can be 1? It might happen that this
So
pile has
all
4
2
cards.
are in.
Right,
Yes,
all
sir.
are the 2, 2, 2, 2. It might happen that. So therefore, in that case, you have only single edge there. Right? Now, if suppose you have some other piles, suppose this is 2, this is 2, and this contains 2, and this contains only 1, 2, then you have this. Okay. So therefore, the degree of these points will be either 1 or 2 or 3 or 4. It can be at most 4. Okay. This is the idea of this. Now what we want, so we want to select 13 cards of different rank, okay, from each pile. So what we want to select one card from each of the piles right hand side of different rank. So that's mean what we actually want, we need a matching. We need a matching from this to this. So suppose there is a matching of this, so this, so this, so this, so this. So that's mean we are taking 2 from here, we are taking 5 from here, we are taking 3 from here, we are taking 4 from here in this way. We are taking 10 from here. Okay, so that's mean we need a matching from L to R. We need a, in fact, we need a perfect matching. Okay, now what is the guarantee that you have a perfect matching? Now here we use the Hall's marriage theorem. So we proved that this is a bipartite graph, obviously this is equal to this. Now we claim that for every S subset of L, we must have this. Now if we can prove this, so that's mean you have a perfect matching and therefore you can choose one card from each pile such that 13 cards contains exactly one card of each rank. Or in other words, you can choose 13 cards from each pile show that the 13 cards are in the different, you can choose a 13 different card from each pile. Okay. Now we will prove this by induction, by contradiction. So if possible, for one S, gamma S is strictly less than S.
Sir, can you please repeat the statement what we are going to prove now?
So this one or this one?
So, sir, in the proof, so this one is what
This
how
one.
we are going to use. No, in the proof, how we are going to use it.
Okay. Now we will prove that for every S subset of L, gamma S bigger equal to gamma, the kinetic of gamma is bigger equal to kinetic of S. We will going to prove this. Okay, so how we will prove that? We will prove by contradiction. We assume that there is a set S such that gamma S is strictly less than the kinetic of S, and we get a contradiction. Okay, so we assume this for a S and we get a contradiction. So therefore, for each S, we get this one, and therefore by Hall's matching theorem, we have a Hall's marriage theorem, you have a perfect matching, and therefore you can select 13 different cards of each different rank. Okay. And how we will get the contradiction? We first assume that this. Okay. So therefore, the neighbors of S has less than n vertices, where n is the cardinality of S. Now what does it mean? That's mean the number of total piles that contains all the cards of each rank or each of the n ranks is less than n. Okay. So therefore the number of these piles is at most n minus 1. But we know that each pile has 4 cards. So therefore this number of piles contains at most 4 into n minus 1 number of cards. But the number of total cards in S is 4n, because we have for each rank you have exactly 4 cards, right? So therefore the total number of cards of from those n ranks is 4n. So therefore this is a contradiction. So therefore the neighborhood S should not be less than the number of S. Okay. So what we are actually doing, we are just counting the number of cards. So first we assume that number of S is n. Okay. Now if possible, number of gamma S is less than number of S. Then the number of piles that contains all the cards, okay, from the n rank is less than n. So for an, you can take this by example. Okay. Now take S equal to say 2 and say 4. So this is your S. Okay. Now what is cardinality of S? That is 2. And we claim that, so if possible, that is strictly less than S, 2. So that's mean it can be 1. Right? So that's mean 2 and 4 goes to the same one. And this means, so this means, see, 2 and 4 has the same neighbor, only 1, right? Since gamma is 1. So therefore 2 and 4 has the same neighbor. Okay. So in other words, it means that these piles contains all the cards of rank 2 and 4. But that is not possible, right? Because that piles have only 4 cards. But total number of cards of rank 2 and rank 4 is 4 plus 4, 8. So that is not possible. Is that clear, the contradiction?
Yes, sir.
Okay. So you can take another one example. You can take S equal to say 4, 5, say J. Okay. Then this equal to 3, and if possible gamma S, it is less than S, that is 3. Say that is 2. Okay. So I have taken 4, 5 and J. Okay. So say this one, and this one contains this 4, 5, J. So these two combines taken all the cards from this one, since these are the only neighbor. Okay, but you have 4 cards here, 4 card in this rank, 4 card in this rank. So you have 12 cards of the rank 4, 5 and J. But here combined you have only 8 cards. So that is not possible, that these two piles contains all the cards of rank 4, 5 and J. So that is not possible, since you have only 8 cards in this two piles, right? So therefore we are saying that number of S, this is not possible. Okay. So therefore that gamma S should be bigger equal to S for each S subset of L. Okay. So therefore by Walsh-Marriage theorem, right? Yeah. Marriage theorem. There is a perfect matching. In G. Okay, so we are done.
Sir, how exactly the perfect matching is solving this problem? I'm not getting the intuition of that. It's like we can have we can have two piles with what I want to say.
Okay. So what do you mean by a perfect matching? Okay, I'm just taking only 4, 4. Okay, then it will be clear to you. So instead of 13 pile, you have just 4. Say 2, 3, 4, 5, and you have 4. Okay. Now suppose you have a perfect matching. So that's mean you have a edge between this one. Say this, say this, say this, say this. So this is the matching. Okay. So that's mean from here you take 4, from here you take 2, from here you take 5, from here you take 3. So you choose 4 cards of different rank from these 4 piles.
Okay. Got it.
Okay.
Okay.
And similarly you can do for the 13 piles. So perfect matching will be enough for this one. Okay, so this is the application of the Walsh-Marriage theorem of the first version. But here I did not include any application of the Walsh-Marriage theorem of the second version. Okay, you should look at for the second version as well. Both are very important. Okay, so we can stop, I think. So this was the last lecture.